Okay, so welcome back to the afternoon session, and this is mainly for discussion of the tutorial. But what I'm going to do is I'm going to take maybe 15-20 minutes to finish off things we've been discussing this morning. And so going back to the Coleman transform, I said that this MPC or multi-blade coordinate transformation can convert the time varying matrices into time invariant form. So we have a system of differential equations with constant coefficient. And the way this is done is by the use of this P matrix. And the P matrix is basically used to transform the problem to a different domain. And then in that domain, we have the time invariant system. However, bear in mind when we look at the physical system, then we have to bring it back again to time variant. So if we consider our new coordinate Q as PT times Q in R. So basically Q in R is the non-rotating frame, and Q is our original generalized coordinate. So obviously with this P transform, we are transforming it to a non-rotating coordinate here. And with this, if we pre-multiply both sides by P inverse, then Q non-rotating is P inverse Q. And by using this, then substituting this P times Q in R in place of Q, and then pre-multiplying both sides by P inverse, we get this equation, which eventually leads to a system of time invariant system. So we now look at our matrix P. Obviously, there's something we see that is, if we take the derivative of P, then P dot is omega P1. Now we have to do that because obviously, if you look at the last equation here, so we have differential of P times Q. So obviously, we have to take a derivative of this. So P Q plus P Q dot. So P dot comes into the equation. That's why we are differentiating P. And P dot is omega times P1. The P1 is this matrix. We differentiate it twice, then we get omega dot P1 plus omega squared P2, which is here. These will actually appear in the term. So once we substitute back in the original equation, the expressions for P dot, and so on, then we get something like this. Because of these differentials, we get these terms here. We have pre-multiplied both sides by P inverse. So eventually, we get a matrix. The first term here will be P inverse in, let's see, P double dot, associated Q and R, double dot, and that is our MC matrix. So this is actually matrix which is not associated with Q double dot. Similarly, if we take the Q in our dot, then there's one term associated with P inverse P dot, and there's another one associated with C times P. So effectively, we get this matrix here. And similarly with the K, we have a matrix here. But MC, CC, KC, they become the time invariant. The right hand side is the external forcing vector. And the time invariant matrices now are given here. You can see. All the matrices are Q symmetric. Like here you see damping. is positive here, negative here. So this is actually a confirmation that energy is conserved in the autonomous system. So this is actually an evidence of that, as you know from basic. So next we use the blade element momentum theory, which we have already studied yesterday and today. And then we take the properties of the blade, the geometric characteristics of the rotor, and the wind speed and velocities. And we do the same thing as we discussed this morning. And if we do that, we get the load. So this is actually the load that we have coming from the blade. If we integrate the load on the blade, we get the total load. But we also have to take into account what is called the generalized loads, because we not only want the loads, but we want them actually associated with the mode shapes and modal loads actually. So that has to be obviously properly accounted for, but that comes from the original equations we derived this morning in terms of the partial. But the load from the wind obviously will follow the exact same procedure that we discussed. So I'm not going to discuss this once again, but you know this with appropriate corrections and so on, like the patterns from towards correction. And then here we did a study based on only the first mode shape of the blades and the tower. So basically a 4-degree of freedom system. And then we can write this in a state space form. So if you take your system, which is a second order differential equation, and if you consider your states as the displacement and velocities like x and x dot, then obviously from the 4 differential equations we have for 4 degrees, we'll have an 8x8 matrix. And the state now will actually consider the displacement and velocities of the blades and the towers. So you have an 8x8 matrix in this particular nature of the matrix. And this is your x dot. A is your state vector, and B is your control influence vector, and B is actually control influence. In this case, U comes from the actuator force that we use to control the vibration of the system. Now, our objective is to determine a gain matrix such that the gain matrix, when applied to the state, so we are assuming that we can measure all the states, or in other words, say the displacement and velocities are known. If they're not known, they'll have to be estimated. So it's an estimation problem then. So we have to derive the x and x and x dot from maybe if you have acceleration measurement, then you have to integrate it once and twice to get displacement and velocities, or velocities and displacement respectively. And once you have that, then you apply another matrix to it, and that gives you force that needs to be applied to solve it. That's what we want to minimize, and that is actually a quadratic cost function. This is, in this particular case, this is a linear quadratic regulator problem. Regulator, again, as we discussed yesterday, is regulating or regulation of certain quantity. And in this case, what we're trying to do is to minimize this, or try to make it as close as possible to 0. So that's why it's a regulator problem, a linear problem, because obviously we're taking linear combinations of 2 variables here, and they are in quadratic form because you see x and x appears here, so it's x squared, u and u obviously gives you u squared. So in the term here, we have the states. We want to actually minimize the response, so x and x dot. Displacement function. So obviously you can minimize certain things by applying a large amount of force, but that's not the idea. We want to actually minimize with an optimal amount of force. That's why this is called quadratic optimal problem. So we want to optimize this, which is the integral of these, and find out the appropriate value of g such that this would be actually minimized. Now, to do that, we are using 2 other matrices. So bear in mind, these are all matrices we are dealing with. So R1 and R2 are 2 matrices, and obviously they will have to be chosen. Now, R1 and R2 will depend on how much emphasis we want to put on minimization of the response and how much energy we actually can spend. And sometimes the energy is restricted because you're using an actuator, you have a limit on the capacity of the actuator, so you can't put arbitrary force or consume arbitrary energy. So there may be additional constraints as well, which you can put in this equation. Now, obviously, this problem is not trivial to solve, particularly with a system like we are dealing with, where we have a wind load as an excitation, because we do not know what the excitation is going to be. And then we can solve this problem in another setting called the model predictive control. And we have done some work on that as well, which I'm not going to discuss in detail. But the model predictive control actually takes into account the wind load that comes in and the model itself and the response, and based on that, it tries to control. However, in this case, we will be accounting for the external disturbance explicitly in terms of the design of the controller. Of course, they'll be minimizing excitation. But there's also other techniques called disturbance rejection, which are also used. But again, I'm not going to go into all the details here because obviously we are course control theory. But anyway, just to give you an idea that then once we get these matrices, we put this into this equation, and then we want to minimize. So it's an integral function we are minimizing. It's a non-linear function, obviously. Now, the solution of this is not easy. However, if we assume that our time frame we are considering is infinite, which is not, of course, again, an approximation that we have to solve for optimization that leads to an algebraic problem. Otherwise, if you have a finite time, then you have a differential problem. So a differential equation to solve. Minimize the objective function, then we can solve it by solving an algebraic equation called the Descartes equation. And if we use that, then obviously we can find out the gain matrix from there, provided the state matrix A and the control influence matrix B is known to us. So this is our A matrix. You can see with A and C in it. This is our X, which is now converted from the non-rotating to the rotating coordinate, because always we have to go back to the original state here. And essentially, this is the set of equations we are considering. So this is the constraint, actually. This is the constraint. The integral function you saw is what we want to optimize, subject to this constraint. So again, if we convert this to the non-rotating frame problem and solve the control problem, because we can do that in the non-rotating frame, once we get the control matrix, we have to then revert it back to the rotating frame. So what we do here is this is our, so this is the A matrix and this is U. So what we do is this is a control matrix B, basically coming from 3 actuators of the 3 blades. And in the non-rotating frame, we solve this problem first because it's time invariant. So for that, we can solve the optimization problem, and we get a gain matrix T star in R in the non-rotating frame. Now again, obviously, this is the problem we are solving in the non-rotating frame. Once we have solved this with this by using this P transpose P matrix. So P, obviously, you know that relates to the P that we use for transformation, and that's been again, yeah. So this is your control input, which is in the rotating frame, and we write that in the non-rotating frame by PU times U and R. This is your U matrix. So once we obtain the U in the non-rotating frame, we have to get it back into the rotating frame. So we apply the U on that, and then effectively we get this minus PU G NR star X NR from the U and R. And then obviously X NR also can be related to rotating frame, which is P inverse XT. So essentially now your rotating frame control input, which is the force we apply relating to the rotating frame displacement and the velocities, which are the states. So really, this is what we are measuring this is what we want to apply, they are related by this transformation minus mu GNR star P inverse. And this now you can call it G star phi phi or something. But you can see that we have taken the non-rotating frame and then converted that into the rotating frame. That would be so that's really what we have done here, and it shows you why this sort of modeling that we have done with the oil electron is very useful, because then you can directly use it and solve the optimal problem. A note of caution, this solution of optimal control law is again not trivial. As I said, like in the case of model predictive control, or there is also a robust controller, there is a technique called linear matrix inequality, which you can solve. So you can convert this problem into a set of matrix that you want to actually look at and minimize under certain constraints, and you can have certain solutions. So there are various ways to solve it, and eventually, in general, they'll lead to some kind of nonlinear optimization problem. So that's because the convergence may not be guaranteed, and you're doing this in real time. So if you do not actually have a convergence, then you're in a problem, right? So that's actually where the key research direction is going towards. So how to solve this kind of complex nonlinear optimization problems. So this is just a schematic wind load and PEM and gravity. We have considered the blade, wind turbine blades and the tower and the controller with this regulator problem. And I'll show you some results. This is actually a 5 megawatt wind turbine blade characteristics, actually a real blade taken here. And these are the two mode shifts we have computed along the length of the blade, the first and the second mode. In fact, it's called modes or B modes. And I'll actually show you a website which is from National Renewable Energy Lab. They have some codes which you can use for getting mode shifts or running neuroelastic codes and so on. But obviously, various companies, various organizations, they have their own aeroelastic load. Like there's a code called Bladed. There's also a code by Rizzo. There's a code by, I mean, almost all groups will have their own codes. So you can get the mode shapes, and this is also really available. This is software where you can use it, but I'll give you also an Excel spreadsheet where you can use some matrices and obtain the natural frequency and mode shapes as well. In general, for tower and blades.
So now bending modes. Are these the bending modes?
Well, in this particular case, so these are the mode shapes corresponding to the first and second modes. Now this blade has a pre-twist, so there's no pure bending mode actually. The first mode will have some the clockwise mode will have some component in the edgewise direction. The edgewise mode will have some clockwise direction. And we have actually, not in this one, but another paper in Royal Society we published. I'll give you a list of few key papers we will follow, where we did look at this coupling of the modes and the twist actually. Because if you have this, then there will be also torsional modes coming. But if you want to get that, then you cannot use Bernoulli Euler beam equation. You have to use shell to model the plates as well. Now this is the aerodynamic load we have for the 3 blades, and on the tower, based on the calculations, this is the BMPEM, which we saw this morning. We have accounted for the linear wind shear along the rotor plane. And then we have looked at controlling the vibration with various kind of, we use 2 parameters, R1 presents the control effort that we are putting in. And obviously, if you have higher control effort, which corresponds to lower value of gamma, so that this gamma is actually the weight that we put on the control effort, so that if it's very low, then then we want to optimize the response irrespective of whatever control force is needed. So therefore, so we have two quantities to see that if you recall the integral we had. There was U transpose, say, R1 U, and then there was also X transpose actually. So first R1 X, and then this was so this was our functional J. So we have two weights of R1 and R2. So if you put a very high weight on this, that means obviously this is not so important. The control force is actually the important thing. If you put a very high weight on this, then this is important. This is not. So that means if you put a low weight on this, the control effort is actually not considered at all, and we apply whatever force is needed to control the response. So effectively, low value of gamma means in this particular case we're getting a higher response reduction. So that means in this particular case we are using that gamma on this control effort, and the low value is used. That means we are not considering whatever is the control effort required. We really want to reduce the response, and that's what is shown over there. So in that case, what we're getting is a significant reduction in the response of maximum displacement and RMS values as well. So if this is the control, you can see a significant reduction is possible. And these are some time history responses. So black one is under control. These are controlled with various weightings. So these weightings correspond to various forces that we apply for the actuator. And this is a spectrum of the response showing that okay, there was a control one, there's a peak over here, and you can see that 0.2 hertz is the rotational frequency. So obviously you have peaks corresponding to so this is around, there's a peak here, there's a peak here, there's a peak here as well, and so on. So you can see that 3P, 6P, these are actually this 1.2 hertz roughly. So 3P, 6P, and then 1.8 is here. So this is 9P. These are actually showing up in terms of the frequencies in the control response. They correspond to the rotational speed of the blade. You also have some tower and blade response, I think, showing up here somewhere. And once you control it with various weighting, you can see there's a significant reduction in the control frequency region. And there is also some peak over here, which is also significantly reduced, but most of the energy in this particular region has been reduced. Also in the low frequency region, the uncontrolled is the black one, which has a value somewhere here. It's a log scale. You can see the blue one and the red one, they're significantly controlling the low frequency response as well. So obviously, all the peaks are being suppressed, and time history we see that this is happening. This is the response from the nacelle, which is also controlled, but not significantly because the controller is not acting on the nacelle; it's really acting on the blades. So I think that's roughly what I wanted to say here. Now, we did also compare with other control strategies, like there's one where we use the velocity feedback, direct velocity feedback. It's another way. So what we do is measure the velocity and feedback something like velocity, and that actually adds damping to the system. And we found that our previous LQR that we have is better than velocity feedback. And also, we compared with our MBC-based LQ problem, the nominal LQ problem. The difference between the two is MBC-based transformation takes into account the rotational structure of the matrices. There's another way you can do it is just freeze the matrix at a certain point in time, and based on that, you design a controller and apply that controller. So we don't take into account the time varying nature of the matrices. And in that case, obviously, the performance is not so good. See that it is working still, but compared to the MPC, the nominal one is relatively inferior, but both actually works. And this again, the nominal controller. Yeah, so this is the direct velocity feedback. See, the direct velocity feedback is also able to suppress the vibration, the response. What happens is you have actually a non-zero mean value in the direct velocity feedback. That shows up over here in low frequency. That is completely suppressed by the controller we had here. But these are some examples to show that various control schemes can be actually used with various different applications and both pros and cons, advantages and disadvantages. So I'll just quickly, these are the amount of forces and so on, so I not use, but a significant amount of reduction has been achieved, like 56% in RMS and 85% reduction in acceleration, and then it's also maximum peak-to-peak dispersion used by 74%. So you can see that this has been achieved by applying a force which is only 28% of the blade weight can provide this sort of reduction. And this is the reference if you want to have a look and go through it more in detail. I think these are all given over there. So this actually brings us to the last bit of thing I wanted to say. And I'll just mention this because I'm not going to go into the detail of this modeling. But as I said, I might give you one cell sort of calculation sheet where you use it. But typically, I mean, to approximate behavior, you can actually use finite element method to solve the problem. And you know that if you anyway, it's an approximate technique to solve partial differential equations. And normally, what happens is we discretize the structure, the element like the towers and blades, which we have been discussing. And this is actually an example where we have shown a tower of interface discretized using Euler-Bernoulli beam elements. But we can also use shell elements, for example, the Reisner-Milling shell element and so on, to do the discretization and modeling. And if you do that, then obviously, first of all, you develop the local matrices, and this is what you have for the beam element, the usual beam element. So you have 4 degrees of freedom each element, so it's a 4x4 matrix. And then you can have potential energy of formulation. So this is the total strain energy here, U, and obviously that is given by half epsilon transpose epsilon V over the whole volume of the system. So I think this is something quite trivially known to most of you in a formal way. So this is your strain energy. So from here you can get the stiffness matrix local. Once you have the strain displacement matrix, from there you have the B matrix, and you can then use this in your potential energy formulation, or the variation of this, or you can also use virtual work and then eventually get the stiffness matrices. And then eventually we take the local stiffness matrices and connect it to the global one, and then form the equations which we solve in terms of K times T equal to F, and that gives you the static solution generally. In the dynamic case, obviously, you have to also consider inertia, but typically the bending stiffness Bernoulli Euler beam element would give you some results like this, like bending moment is EI into UDZ2. So in this case, you look at the shape functions and appropriately find the B matrix, which is the strain displacement matrix. So this is again giving the shape functions, or basically Hermite polynomials, as you know, for beam. And this is the matrix here. And this is actually what NREL, which is, as I said, the National Renewable Energy Lab in Colorado and US, they use for their beam modes. Like the one I showed in our blade calculation was using beam modes in that. And so obviously, if you're using this, you can't account for the pre-twist as you were asking. So But we have done some other work with shell as well, where we could have other actions. So then local to global, again, I'm going through this very quickly. And then this is an example where you have the local matrix. It's just two elements, and then it shows how to actually appropriately assign the values to the various boxes in the matrix here. And once you have the global matrix, obviously, you have the full matrix. You can actually then proceed with the solution. And for the dynamics problem, as I said, you also have to consider the inertia and appropriately then consider the mass matrix. And there are various ways you can have the mass matrix, like you can have the lump mass matrix. You can also have mass matrix which is consistent, or you can derive the mass matrix based on some continuum approximations as well. So once you have brought the equations, the stiffness matrix and the mass matrix, either lump mass or consistent mass matrix, then to solve the mode shapes, we usually ignore the damping part and then proceed to solve this equation, and then eventually we can get the natural frequency and mode shapes. So this is a paper in wind energy again published, where we get a finite element model of a pre-stressed or post-tension concrete wind tower. We've done work with the hybrid tower as well. So it's a partly steel, partly concrete. But here we are using the shell. This will give you some idea about also how to use the intermediate reinforcing bars, or if you have this stiffening elements, and how to consider those, or if you have to look at thermal effects or long-term effects in terms of strain, relaxations, and so on. All those things there as well. So you can make it complicated, but then finite element is, like, in general, finite element is not different actually for wind turbines anyway. So you can use this for towers, you can use it for blades, and appropriately design your. There's also another work we did, which is another paper in engineering structures, where we also modeled the drive train and the variable speed. Another paper in wind energy we looked at also the connection with the grid. So I'll give you a few like list of those which you can follow. So I think this is the end of what I wanted to say till this morning, but I took up another half an hour this afternoon, and I took the liberty of doing that because I think we're discussing assignment 1 today, which is not going to take 1 hour possibly, but I'm free to answer any other questions you might have. So thank you. So I think they'll reorganize the whole thing, because they'll be now also focusing on you. So there's a change of focus from now on. So I have spoken enough until now. It's your time.
So the load is assumed as UDL over the pin plate.
Over the
Pin plate.
plate? No, not you, because you saw that we are calculating this PN and PT, or PC and PD and PL. So obviously that's not uniform.
So when you solve the so what have you taken on the right hand side?
You mean the problem that I solved?
Yes.
Yeah. So that has various components. First is the wind load. So wind load has a wind shear and turbulence. And that actually then is used in the blade element momentum theory to compute the loads on the blade. Okay. So obviously, based on that, whatever load comes in is the load. Like based on En and Et, you can find out the normal and the tangential load. So it would be a load which is time varying, but spatially varying as well, because Pn and Pt, they are functions of time, but they're also functions of R, which means the radial distance from the hub. So it's actually at a location what the load is. So it will be varying along the length of the blade. But when we actually take the generalized load, so what you ask on the right hand side, then what you do is you use the virtual ward. Essentially, what will happen is the mode shape comes in as well. So that actually is the modal load or generalized load.
We are pre-multiplying that by transpose.
Yeah. Yeah. So you have to formulate the virtual ward, and we have that in our question as well. So that is the main load, and then the gravity load also is there. And the only point load is the actuator load, which is acting at the tip. So that's why
we get to consider all these loads.
Yeah.
In the Gallatin formulation,
So the two formulations we're talking about now. One is the Euler-Lagrange formulation, which is based on the stationary principle, and then you actually obtain the equations which are discrete equations, so ordinary differential equations from there. The one we discussed here now in the finite element, in the first is a free vibration problem. We get natural frequencies and mode shapes, which are then used in the Euler-Lagrange equations. That's one. You can also use the finite element problem to get the dynamic response as well. But in that case, then obviously your mass matrix and sequence matrix, they're all there. And the load matrix would be on the right hand side. In that case, you do not take the generalized load. You still use BM on the blade, for example, and get the nodal loads, but then the nodal loads will be appropriately transferred to get the equivalent nodal loads for the FEM formulation. This is for the main load. Same for the gravity and so on. For the tower, basically what you then have to do is you have to again take the wing load along the tower height and get the nodal loads. But if you look at the loads, like the blade, obviously the rotor area is significant, and it's at much higher elevation than the tower. The total load that acts on the wind turbine is really the load on the rotor actually. The tower load is small, maybe 10–15%. Most of the load is on the blade.
So while we select the airfoils for the blades, so we know that airfoils are basically selected based on the Reynolds number.
Yeah.
So when we consider a blade from the hub to tip, since it is radially varying, so even the Reynolds number at each station is varying.
Right.
So there is a little bit of confusion or kind of skepticism. Which airfoil related to what Reynolds number we take, because all the airfoil data for all the Reynolds number is not available. Simulated also takes a lot of time.
Yeah. So basically, if you look at the so normally what they do is so for a blade, if they take an airfoil section, the airfoil section doesn't vary along the blade, so they scale up or down depending upon what location it is. So the chord length is varied, and appropriately the airfoil shape is scaled up or down. But the airfoil is the same. Now, what the question is that if we look at the Reynolds number, and the chord length is varying, obviously, the velocity and so on. So your Reynolds number is varying. Yeah. So what you're asking is that how to choose the proper airfoil. So the answer is that if you look at the generation of the power, most of the power is generated because of what happens near the tip, and the load is near the hub. So basically, you choose something that going to be representative of that region where most of the power will be generated. So typically that's how it's done. But the cross section for airfoil for various wind turbines, like the 5 megawatt one, 2.3 or 10 megawatt, they are more or less fixed. And don't much experiment with the airfoil or optimize that in that sense.
Answer might be suitable for a multi-airfoil blade, but if you are designing any blade with a single airfoil, then will that suffice the entire requirement of the power generation?
No, the short answer is no. But that's what I said, that you choose the airfoil so that the corresponding Reynolds number you expect in that region would actually give you the power coefficient that you need or the lift that you need. So what I'm saying is that you know that most of the power is going to be generated near the So if you choose, say, a location which is say 7% from the up, calculate the Reynolds number over there, then that particular Reynolds number will govern what airfoil profile you'll be choosing to get a certain amount of power or lift actually. But I don't think that's the only consideration. There are a lot of other considerations for design of or choice of a particular airfoil for a particular turbine.
Wondering, show the diagram with the LQ controls, LQ controls and the uncontrolled graph. And there's a peak in the lowest frequency range, but it's not suppressed, and you suppressed the next frequency.
Yeah.
But when you look to the magnitude, the lowest was higher than the second one. So why is that?
So the low frequency corresponds to what is called a static or a quasi-static response. So a quasi-static or static response can only be suppressed if you can apply a static load. So that cannot be suppressed by any of the classical vibration control strategies like tuning or
there's no much difference between the frequencies. Like because the scale you give is
it's a long scale. So you mean the horizontal frequency or horizontal or horizontal?
Horizontal is hertz.
Yeah,
It's not
horizontal is linear.
linear, so the hertz are actually not much different because
Yeah.
one is at 1 point something and the other is at 0 point something. So, so what made separation? Because generally for a mechanical devices, the resonance happens at the higher frequencies. But here I see you want to suppress that frequency, mainly considering it as resonance. Is that the
No, the resonance is not the criteria here because we have no tuning criteria here. So resonance is not the criteria. And what really we're doing is we're just minimizing the total energy, obviously, because it's an optimal controller. And the lowest frequency or the low frequencies are not suppressed that much because obviously to suppress that, you need a large amount of force to apply. But we're still able to do that because we're applying an actuator force at the tip, so that still actually suppresses some of the static response. So if you look at the controlled and the controlled one, that is still suppressed. And you're of course suppressing the other responses like corresponding to the blade and the tower. I think one is 1.5%.
so which means this controller is not can suppress some of the peaks,
Yeah.
but not the very low frequency vibrations.
It can, but then you need a very large frequency, large force to do that. So,
So when we determine the performance of a wind turbine analytically and under the influence of random tip losses, the last element, the element at the tip will produce zero power, zero forces, zero torque. So is that primarily due to the complete flow, the flow that is completely separated, or because of the flow losses that is happening at the tip?
yeah, tip losses are significant actually.
So only because of the tip losses it goes to zero. So that is the only reason.
Yeah. In fact, if you do some numerical calculations for this BEM, you might have a problem with convergence actually with the tip. But because, as you said just now, that because the power is zero and loss is zero, you can force it to zero, ignoring that part. Sometimes you're doing BEM and you might have a problem with convergence. You find it's because of that region, the whole thing is not converging. In that case, you just ignore that. But assume that there's no tip in the blade. If you can have a blade without any tip, or a finite blade without any end. So I think we have another 10, 15 minutes. So do you want to discuss the assignment now, or do you have any questions, or you're more or less clear with that? Or need more time to look at it?
Sir, why does the thrust coefficient remain constant for a particular range of wind speed? From 5 to 8 meters per second, the graph it's like almost constant. So why for that particular range then there is sudden drop.
Which graph is it?
CT versus wind speed.
CT versus wind speed, not CT versus A.
Wind speed.
But CT versus which, do you have a particular drop?
For any wind turbine,
Yeah.
we have power curves and
Yeah.
CP versus wind speed.
Yeah.
Now thrust coefficient versus wind speed. Initially, the thrust coefficient is very high for lower wind speed.
Yeah.
And then for a particular range of wind speed, it remains constant.
Constant.
Why is that so? For only that range of wind speed, and then there is a sudden drop.
So your question is why the thrust is not increasing velocity?
Yeah.
Maybe you're referring to some graph here. So, yeah, technically speaking, if you're so first of all, for the ideal rotor, the thrust coefficient is constant, like 8/9. That's the CT you get.
Sir, actually, it's not in the matter. I have seen on one of the websites for Siemens wind turbine. So along with the power curve, there was a curve between CP
Oh,
and
okay, yeah. So probably they're using the pitch control there. So if you they're controlling the pitch as well. So the pitch control also has the effect of controlling the aerodynamic load. So obviously, if you increase the wind speed, your load keeps on increasing. But if you change the angle of attack, then you can change the load by changing the pitch. So probably they're using some control there to keep that at a particular constant value. Does it answer your question? Possibly. I don't know exactly what you're referring, but I guess that is what they're doing. If you're talking about some website data or some graph you've seen, Siemens, so probably they are using the controls as well there. Because typically for high wind speed, they don't want the whole thing to get damaged and so on. So probably, yeah, they do something with that. I'm trying to find the graph of one graph because no, we only have CP actually, not CT.
For the modern predictive control,
Yeah.
I gave a reference load that for tracking the for the controllers to track. It's the ideal data which you use. So you mentioned it as the wind load and the other powers. So because since it is moving, how do you actually calculate it? I mean, how do you take a reference that?
No, so for the model predictive control, what we do is, first of all, we need a model. The model we use is basically the wind turbine model because we have the model, so it's ideally suited for model predictive control. So then once we have the model, we then can actually use the model to predict the response, obviously. And for that, we then take into account the excitation load that's acting, which is the wind in this particular case, to get the response. And with that, then we have to satisfy certain constraints, which are, say, the blade displacement will be certain value, power will be generated within certain limit, the speed doesn't go beyond this, and all those things. Tip speed ratio is within this, and so on. So all those things will have to be satisfied, and then we have to minimize certain things. And that could be the response, could be your maximizing power generated, minimizing power, or even if you have economic value, then we put that also, we get what is called the economic model predictive control. You can also take into account the uncertainty, like if there's a change in frequency and some things, you can put that as bounds there. So all those things can be done.
Generally, we have a reference, certain reference which this controller have to run. That's
not necessarily for the model predictive control. You have to have a model, and that will be the constraint that has to be satisfied, the differential qualities or inequalities. Then you can also have some algebraic inequalities. Like I said, the speed will have to be within certain range, the powers will have to be within certain range, the acceleration, all those things. Control force within certain range, pitch will have to be within certain range. And then based on that, you say what our intention is to maximize the production of energy, say. And then you have that a functional. And then you can also put, like if you say, oh, instead of that, I want to actually maximize the amount of money I earn. And say, I get a certain amount of money if I feed the power to the grid in the morning, and sometime in the night it's actually different value. And those can be also put in, and we get an economic model control. And then we need to solve that by some optimization technique. So again, it comes back to what will you use this optimization technique will you use to solve this. So you can cast the whole thing in an MPC format and then solve it. Like here, the LQR, the gain was calculated at trial. That's it. But in the MPC, you will be calculating the optimal solution in real time. Okay, so yes, I mean, you can finish off a few minutes already if you don't have any other question. You have. Did you try the assignment one? So you have a question on the assignment? Assignment one? You can come to the board or you can tell us from there. Just before I forget again, just to remind you that the exam will be tomorrow, 4:30 to 5:30.
Sir, actually in Rayleigh's and Weibull distribution, I'm getting Rayleigh's distribution curve is much higher than Weibull distribution.
When you say higher, what do you mean?
Higher in speed distribution.
Okay.
PSD actually. PSD. Over distribution curve, I can actually show you.
So you have used some data, and then you have estimated the parameters for the Rayleigh and the Weibull distribution, and then you have two PSDs. And then what you're saying is that, and then what was your next point?
Actually, sir, I got one function using method of means on distribution that is matching with Weibull's distribution.
Okay.
But it is not matching with Rayleigh's distribution.
No, but if you have the mean, you can always, okay, what you're saying, I understand. If you take the mean and then plot the Rayleigh distribution, it doesn't match the histogram very well. Yeah, that's fine. That's fine. So if it matches with Weibull, that's why the Weibull is preferred. It has better flexibility in dealing with various distribution density functions. That's a good conclusion. That shows that why we need two different density functions and so on.
There is any specified standard deviation range? Like I got 1 point something. There,
It will depend on the data here.
Yes, it is mostly dependent on data, but still, like in custody, we can get much more standard deviation maybe. But there is any conclusion like 10% maybe, like something like that.
Well, I mean, if you have a Gaussian distribution, we know that the various percentile that we have with sigma to sigma to sigma. So we know that 3 sigma is how much? 98 point some percentile. Sigma mean plus sigma is 67%. The area under the curve. Okay, so it seems like you've done the assignment one pretty well. So well done. Do you have something more to answer?
So in the case given, A what we achieved.
Okay, so we can still keep on interacting on that. But it's just call it a day and stop so that you can turn off the camera.